Hey all, Rusty Rob here. Welcome to another video. Let's go through the Hacker Cup 23 practice round, the road to Nutella problem. So a super hard problem here. You're given a whole lot of graphs, and each one you're given a whole lot of queries. And a query consists of a start node and an end node in which your friend just walks left foot, right foot, left foot, right foot along the shortest path to their end node. Whereas you take a different path so that you want to end up at the end node with a different foot reaching the end node first. So if they ended up with their right foot on the end node, then you want to use your left foot on the end node. So you can see that here. And your foot's always going to be in sync with your friend, really, unless you can find an odd cycle, and that's going to kind of swap your right and your left foot around. And a trick for finding an odd cycle is to do a breadth first search. So you know the distance of each node from the root, and then if there's an edge between two nodes of the same distance parity, then an odd cycle must exist. And then to make things interesting, they say you'd like to minimize the number of edges you travel through more than once. And so that makes you think, okay, bridges aren't great because if I travel through a bridge between islands of the graph, then depending on where the finish is, I might have to come back along that bridge to get to the finish. So ideally, I could just find an odd cycle on the way to the finish. But if that's not possible, then I have to go across some bridges potentially to some other island and maybe another bridge and so on until I find an odd cycle. So then the question is, okay, which odd cycle is closest to the path between the start node and the end node with the least bridges? And so that seems like a really difficult problem, especially since these graphs are really big. There's a lot of them, and then there's also a lot of queries. So we basically need a linear time or an n log n solution. So let's have a quick look. So that initial graph looked like this. Let's change to black. And I think it looked like that, right? Something like that. And so if we use a bridge finding algorithm, then we will see that this is a bridge, this is a bridge, this is a bridge, and this is a bridge. And then if we remove all of those bridges, then we're left with these components here, that one and that one, which are, I guess they're bi-connected components or something like that. And then each of those we could check if they have an odd cycle. So this one doesn't have an odd cycle, but this one does. So we could make a new graph which just has the components. So that graph would look like this. So here you can see this component here is just here. These nodes remain unchanged, they're just their own components. And then these four here would be this component here. And so essentially the only edges we have correlate to the bridges. Right? And so we know this is going to be a tree because if it wasn't a tree, then this should have been a component, right? So we're left with a tree. And so that's nice. Trees are more efficient to operate on So for each node in the original graph, we just map it to a component. Okay, cool. So now what? If we look at which components contain an odd cycle, those are the ones we'd want to go for. So in this particular case, this one's got an odd cycle in it, whereas this one doesn't. So now we've got a tree that has some red nodes in it. And we know, let's say for our particular query, we are starting here and finishing here. Then we basically have to travel along here, right, to get to the finish. It's the only way, since now we've got a tree. And it's going to cost us 1 to go to here. So we kind of want to know along this path, what is the closest red node? And so we could draw that tree slightly differently. So we could have a tree with some red nodes. And we have some 2 blue nodes in a query. So we could say, okay, what's the lowest common ancestor of those 2 blue nodes? So in this case, it would be that. And this could just be a smaller part of like a larger tree. So then we could think, okay, each node has a cost, which is a distance to a red node. So this would be, all the red nodes would be cost 0, right? Whereas this would be cost 1 because it's 1 away from a red node. This would be cost 1, 1, 1, 0, 1. Oh, sorry, that one should be 2, and so on. So we basically just want the minimum number on this path. So in that case, it would be 1. So we could visit this one and come back. We could visit this one, and so on. And so how do we compute that efficiently? Well, we can just depth first search from the top downwards and keep track of these costs in the segment tree. And so as we depth first search, we update the segment tree. And then when we get to a node that is part of a query, we can look at all of the queries responsible for that node, which is a start or endpoint. And from that query, we can see what the other blue node was. And then we know what the LCA was, the lowest common ancestor. So then we can just calculate the minimum from the segment tree and then add that as a potential solution to that query. And later on, when we depth first search to that other part, it'll find the minimum along this path. So each time we go to a new node in our depth first search, we update the segment tree based on the depth. So the root node would be at 0 in the segment tree. The next node would be at 1, depth 2, depth 3, and so on. And the other thing was, how do we know which components are odd? Well, once we've got all the components, we can just start at an arbitrary node in the component and just do a breadth first search. So we know this would be distance 0, these would be 1, 1, and then 1, and then this would be 2. And then you just want to check, is there an edge between nodes of the same parity? So in that case, you can see this edge here is between two nodes of the same parity. 1 and 1 are both odd. So we know that this is an odd cycle here. And so we know this component is odd. And if you think about it, it means there must always be a way to get to that odd cycle kind of for free. And we can always return back to here with cost 0. For example, if we try to think of a way that it would cost us extra, let's say we had a component like this. Let's say this was our component like this, right? Then you can imagine you come in here, you come up here around, and you've gone around an odd cycle, then you have to come back down this edge again. So you think, oh, that's going to cost 1, but actually this would be a bridge here, so this would be an invalid component. So it has to have another connection here, and that means now there's no bridges. But now you could come around here and around here, and either down here or down here. So because there's two options, we know one of them's gonna be odd. So it'll be back here with a different foot, and then we can continue on back towards the finish. Or we could go through it towards the finish. Either we pass through it or we just go back. So yeah, let's have a quick look at the code. See if I can do presentation mode. So this is the code to get the bridges. So we basically just do a depth first search, and yeah, maybe I should show that on here. How do we know bridges? So let's say we have a graph. And let's say we've got some graph and we've explored part of it. And now we're exploring this bit here. So we're kind of doing a depth first search through this graph, and we've come down through here. And it's like, okay, this kind of looks like a bridge, right? But if our depth first search continues back to the graph, then this is no longer a bridge. That's kind of the intuition. So if we kind of keep track for each node we've visited so far, its depth in the pre-order traversal. So if we ever get back to a node that we've been to, like say we've been to here, then we know that this is not a bridge. So that's kind of what this is doing. So we just have the depth and we keep track of the lowest depth of each node and so on. And so what does this do? This is where we store the edge, the bridges. So basically we looked at all the children, and the lowest depth that the child visited was equal to the depth of the child. So that means from the current node to that child is a bridge. This is just breadth first search of a component, which is pretty, and keeping track of the depth. So this is the code that just gets components from the non-bridge edges. So we just building a graph of the non-bridge edges. Then we're just looking at getting the depth of nodes in that component. And then we're just going through all the non-bridge edges and checking the parity. So we know the depth of both nodes on that non-bridge edge. And if the parity is different, then we know that the component's odd. So we just set that component to odd. So we've got a list of odd components. Here we're just reading the graph. Here we've got a query, which is just from node U to node V. And this is the component of U and the component of V. So back over here, like here, this might be U here, and then the component will be this number here. So we just have numbers from 0 to however many components there are in this graph. And here we have numbers 0 to n, and so there's just a mapping between them. So that's what we have like a component array for that. And then the lowest common ancestor of these two, because we're just using this. Once we construct this graph, we just use this to solve everything. Reading the queries. What's this do? This is depth first search. Can't remember what that was. That's just getting the edges from the graph in order so that it's more like a tree, because we have reverse edges. I mean, it's not the best way of doing it, but whatever. So this is getting the component tree. So this tree here. So we get all the edges by reading the graph, the bridge edges with that bridge algorithm I showed you before. Get the non-bridge edges by just any edge that's not a bridge edge. Then we find out, we grab the components from the non-bridge edges and we work out which components are odd. So this is just a mapping for each node which component it is, the idea of the component. Then we build a tree somewhere. Then, I forgot to mention binary lifting. To find the lowest common ancestor, we use binary lifting. Maybe I could go through that quickly. And then this is just the level or depth of each component. So we go through each edge in the graph, but only the edges pointing downwards. So we're just kind of... hang on, my headphones are dead, so I'm going to turn them off. Hopefully you can still hear me. So yeah, here we're just drawing the depth of each component, the parent of each component, and we're building a tree of components. So that's just this stuff. And then we're working out the cost of each component. So that's pretty straightforward. We just depth first search down, and the cost of a node is just the minimum of the node's current cost and the cost of the child. And we do a saturating add, which avoids overflow because these costs default to the maximum U size, and so we don't want that to overflow. And so this will not add 1 if it's already the maximum value. That's a nice way to avoid overflow. And then we go the opposite way, where we make the child cost the minimum of the child cost and the parent. And so we've essentially we've kind of, push these costs upwards and these distances upwards, and then we've gone the other way to push the cost back downwards. So now for every node we have a cost. So this cost vector is now populated. So now we're just going to return all of those. Here's the lowest common ancestor algorithm. So you can look up binary lifting if you want to know how that works. But in log n time, it can work out the lowest common ancestor of two nodes. Just because we pre-compute the parent and the parent's parent and so on. So we can kind of skip, maybe I'll show you that quickly. Like, let's just say you have, you know, a bunch of nodes and each one has a parent. And then if we can skip ahead 2 and skip ahead 2 and skip ahead 2 and so on. And then imagine if we could easily skip ahead 4, right? And then we could easily skip ahead 8, skip ahead 16, 32, 64 and so on. So that's what binary lifting does, is it tries going ahead with really big numbers, and then it kind of matches the nodes up and it finds the lowest common ancestor really quickly. So we've got the tree, the component of each node, the cost of each component, the parent of each component, and the level of each component. And then we've got the queries. If there is no cost of 0, that means there's no red node, then it's going to be impossible because there's no odd cycle. So we just return -1 for every query. What is this? Node queries. That's just working out for each component what queries are important to that component. So we're just going through all the queries. We are populating the component associated with the nodes, and then we're populating the lowest common ancestor of those components using the parent memoized for binary lifting. And then we're also going through the queries and seeing for each component what queries does it have. So given a component, I can easily find the queries I need for it, or at least the index. And then this is the hard part, is this bit here. So we've got a segment tree, which based on this is just the height of the tree. So I just started off with all maximum values, max I64. Then we do a depth first search with the tree starting at the root node. Then we pass in a reference to the cost array, the segment tree, the level, the queries of each component, and the queries themselves. And that is just going to populate the answer in each query. So each query has an answer that's going to be the minimum that's possible for that query. And then we're just going to sum up those answers and return that. And then we're just going to print that out. So let's look at this depth first search. So as I mentioned, it's got the tree, it's got the node, it's got the cost, segment tree, the level, the node queries of each component, and the queries. So we start off at the root node, and then we just go through each child of that node, and then we just depth first search the child. And as we go, we're just tracking the minimum across all the queries. So for this particular node, let's say we're at a particular node that we're doing a depth first search, then we know the depth of that node, and so we'll just update the segment tree. So we know the cost of that node, so just add it into the segment tree. Then we look at all the queries associated with that component, with this component. So the answer to that query will be the current answer and the minimum of that and a query of the segment tree. So we're just looking for the minimum between the lowest common ancestor and the current level. And we just go +1 because it's an open closed interval. And this segment tree tracks the minimum because we set it up here with the minimum. And yeah, so the way that's working is, let's say we're at this particular node here, so, and it knows, okay, a particular query might be this lowest common ancestor, so it's just taking the minimum of here. And yeah, that's pretty much it. So we could run that. So yeah, usually runs in about 2 seconds, so it's pretty quick. So yeah, I'm keen to see the editorial and see how this is supposed to be solved, but that's just the way I thought of doing it. So I hope some of you gave it a try, and good luck for the rest of the practice, and hopefully see you at round 1.